we've seen how to use integration to find volumes and lengths and things like this. We can also use it to find surface areas. Let's have a go at this using solids of revolution like we did for finding volumes. The idea is we take a curve like y equals f of x, rotate it around the x-axis, and that will produce a solid that we could find the volume of, but we can also find the surface area of it. So this becomes some sort of solid like this, and the surface area of this we can find by dividing it into thin strips. Now, if we rotate that strip around the x-axis, what are we going to get? Well, we're going to get a ring of some sort like this, and if we just label on what we're going to find out, what we know about that ring is that its radius is y, since this height here is y, this length in here is ds. And we figured out how to relate ds to the function and its derivative, so the surface area of this is approximately the circumference of the circle times the thickness, which is given by ds. And this we can write as infinitesimal area dA. We've seen how to relate ds to dx, and remembering that y is a function of x, I can write this as, so the infinitesimal area is that, and therefore the surface area is just the integral of the infinitesimal areas. We add them all up, and so we can write this as the integral, and typically we'll be bound between limits, let's call them a and b, so this will be a definite integral, like so. So that's probably a bit abstract. Let's try with an example. Let's try with the example of finding the surface area of a sphere. Okay, well, we know the answer, but let's try and figure it out using integration. Let's start with our generic idea of taking a curve y equals f of x, rotating it round the x-axis in our mind to form a solid of revolution. As we did for the case of finding the volume of a sphere, I'm going to choose our semicircle centered at the origin. So we take the top half of a circle, rotate it round the x-axis. And this is bound between minus r and r. So the area we want to find. So let's just work through this integral and let's substitute for y and dy by dx. So y is square root of r squared minus x squared. Now dy by dx is going to be, so the ds part, the length of an infinitesimal width on the circle, is the square root of 1 plus x squared over r squared minus x squared times dx. Simplifying that, we have the square root of a whole bunch of stuff, which simplifies to, and remember r is a constant, so this thing comes out to be 4 pi r squared, as we would expect. So we take a function, rotate it round the x-axis, that produces a solid of revolution with a symmetry if we slice it up into thin disks. The surface area of those disks is roughly 2 pi y times ds. Add them all up using integration, and we get our answer. Let's have a look at an object now where we look at its volume and its surface area, which is a kind of paradoxical shape. It's called Gabriel's horn. So we get a strange object by taking y equals 1 over x, the parabola 1 over x for x greater than or equal to 1, all the way up to infinity, rotate it around the x-axis. So we rotate it, and it extends all the way up to infinity. So this produces a massive horn. But what's its volume and what's its surface area? Let's take a slice through it. Rotate this around the x-axis, we can find the infinitesimal volume of that. So this gives us a disk, and this disk has an infinitesimal volume and an infinitesimal area. And we can go ahead and now compute both of those things. Let's start with the volume. The volume is the integral of the infinitesimal volume dv, and that is, we integrate over all the slices x from 1 to infinity. And that's equal to pi times the integral from 1 to infinity of 1 over x squared dx. Let's calculate this. So we have pi at the front. We do the upper integral using a limit. So we calculate that limit, part with t tending to infinity, it drops out, tends to 0, and we're left with pi. So the volume of this infinitely large object is finite, and it's equal to pi. What about the surface area? So we have the area is given by the integral over the infinitesimal slices dA. We integrate with respect to x from 1 to infinity. We can only do the integral once all the y as a function of x is substituted, so let's do that first. Y is just 1 over x. dy by dx is minus 1 over x squared, so when we square it we have 1 over x to the 4. So we have an integral up to infinity written as a limit as t tends to infinity. We cannot do this integral analytically, unfortunately, but we can evaluate this limit as follows. The integrand, 1 over x times the square root of 1 plus x to the 4, is always larger than 1 over x. And this implies that the integral of these two functions satisfies the same inequality. And this inequality is true for all t greater than 1. As t tends to infinity, we know that the integral on the right diverges. We've already calculated this. So what does this mean? Because the integral for the surface area of Gabriel's horn is always larger than this integral of 1 over x up to t, this means that that surface area integral also diverges. So if I calculate that limit, that equals infinity. So the surface area of that object is infinite. So we have an object with a finite volume but an infinite surface area. So you can fill this object up with a finite amount of paint, but you can never paint its surface.